The journey begins with index notation, which the sources describe as a transformative tool that converts abstract mathematical identities into physical insights. By utilizing the Levi-Civita symbol and the Kronecker delta, researchers can manage multidimensional spatial relationships and mass distributions. A critical component of this foundation is the epsilon-delta relation, which provides a method to prove complex identities, such as the BAC-CAB rule, without relying on messy component expansions. Furthermore, these antisymmetric tensor products follow a specific dimensional scaling, from a factor of 1 in 2D to 6 in 4D, illustrating how spatial complexity consistently collapses into symmetric, manageable algebraic scales. Building upon algebraic rules, the sources use differential operators to define the pointwise geometry of fields. Divergence and curl. Divergence represents source-like outward flow, while curl signifies local vorticity or circulation. Field categories. Fields are classified as irrotational, conservative, when they have zero curl, like gravity, or solenoidal when they have zero divergence, like magnetism. Second-order identities. The sources highlight the double curl identity, which decomposes the curling of a field into its divergence and its total spatial curvature, the Laplacian. The third pillar bridges microscopic field properties with macroscopic behavior via the divergence, Gauss theorem and Stokes theorem. However, the sources introduce a critical distinction between local and global behavior. Topological quantization. A field can be locally conservative, zero curl, but globally non-conservative if it encloses a singularity, such as a vortex at the origin. This is measured by the winding number, a topological invariant. Singular flux. While standard laws like Gauss's law use an inverse cube weighting, the sources explore a fifth-power inverse weighted fields, where the origin acts as a divergent integral that requires an exclusion zone to maintain mathematical identity. To simplify complex boundary value problems, the sources emphasize selecting the correct coordinate framework. Orthogonal systems. In robotics and atomic theory, orthogonality ensures that Jacobian matrices remain sparse or diagonal, preventing parasitic movements when moving along a single axis. Non-orthogonal systems. In these frameworks, vectors are measured through a dual basis, where dual vectors act as directional filters to recover fixed components even as the tangent basis rotates or collapses. Specialized frameworks. Hyperbolic coordinates are used for Lorentz boosts and fluid streamlines, while parabolic coordinates are ideal for modeling electric field singularities at knife-edge geometries. Finally, these mathematical tools are applied to the forces governing the universe. Work and energy. The sources demonstrate that magnetic fields do zero work on moving particles. They only apply centripetal force to bend paths, as seen in cyclotrons. The uniqueness principle. A physical field is a solved puzzle only when its internal sources are anchored by specific boundary conditions, Newman or Dirichlet. Potentials. The Yukawa potential models the competition between electrostatic attraction and thermal randomization in plasmas. Meanwhile, the Dirac String singularity emerges in vector potentials, proving that a point source potential cannot be globally well defined without a mathematical seam to account for total flux.